Hey everyone, you're watching Computing Science with Justin Woodring. And you guessed it, my name is Justin Woodring. I wanted to talk to you today about the Hadamard gate. Now, the Hadamard gate is a quantum operation that is used almost daily by quantum computer scientists. It's one of the essential operations we use to place qubits into superposition. And in fact, if you watched my last video, learning how to program a quantum computer, your first program, I think the title's a little bit different, but you get the gist. If you watch that video, we actually used the Hadamard gate, and I basically just glossed it over and said, this works, just trust, you know? But today we're going to dive a bit more in depth into how the gate actually works. Now, this is going to be a bit more mathematical, so obviously I'm not trying to scare you away, but if this stuff doesn't make sense at first, you may need to brush up on linear algebra, even though I will try to simplify it as much as possible, especially the more specifically quantum aspects of it. But let's go ahead and dive right in. It's not super scary math if you aren't familiar with it. You know, you can probably brush up on it in maybe 30 minutes to an hour if you're really interested and just know nothing about it at all. But again, we're going to try to make this as simple as possible so that hopefully you won't even need to do that. So let's go dive in, get started, and see what the Hadamard gate's all about. So, to give us a little bit of background first, before we dive exactly into the definition of a Hadamard gate, we first have to establish that how we think of quantum computation. And at the end of the day, although quantum computation relies on quantum mechanical principles, a lot of the math we're going to be doing is linear algebra and probability. So if you've taken linear algebra, even in high school, and some basic statistics, it should be at least enough to get started. So certainly no more than what we're going to cover here. So you can think of basically almost any quantum gate as some kind of matrix, and it's basically affecting a vector of probabilities. So what that means in a more simple sense is you consider you have a coin, right? And you're gonna, let's say, yeah, you want to flip a coin. So if I asked you right now, what's the probability of getting the heads or tails, and you just flip a coin randomly, you would say it's 50-50. So we can take those two probabilities and put them in a list. Now we're going to call that a vector. So we have a vector of probabilities. It's 50-50. Interestingly, the Hadamard gate effectively does the same thing, but we're going to look at a mathematical understanding of why that happens. And although it may not make a lot of sense just watching this one video, as I start to cover other quantum operations in the future, you'll start to develop an intuition about what's actually going on here. So at first, basically our matrix representation of the Hadamard gate is this weird little square box right here. It's the matrix, and it's got these numbers in it. And now these numbers are going to effectively influence the probabilities that we're actually dealing with. So what that means is that when we take our probability vector, which you'll see later, and multiply it by this, we get a different probability vector than what we had before. So imagine if I could take an operation that would take your coin that always landed on heads and then make it, now it's going to land 50-50. You know, it could land on, it's going to land on heads or tails 50-50. And if I apply that operation that I just used again, it's going to go back to heads. It's only going to land on heads ever again. That's basically how the Hadamard gate works. It's doing the same thing. So this math right here, you can work it on a piece of paper. You can type it into Wolfram Alpha or any other random tool if you want to verify my work here. You'll see basically that this is not exclusive to quantum. If you applied this to basically a probability vector of any kind, specifically a probability vector of length 2, which has a probability of getting one result versus the other, then you would you would see consistent results. One important aspect to note is that although this is actually not a complex, none of these are complex terms or anything like that. So, but the quantum probability amplitude vectors can contain complex numbers, so that's just something that may come up in the future. So it's fine, but we don't really need to worry about that too much right now. So moving on, like I said, I've already defined the basic matrix representation of what this is. So by itself, it's just this. If I were to put two of them together, an interesting thing happens. This is the identity. You get the identity basically matrix, which basically says don't change the matrix I'm multiplying it by at all. So if I use the identity matrix on my probability vector, then I'm just going to get the probability vector I put in right back out. And so when I mentioned how if you apply the Hadamard gate twice, you'll end up getting the same thing you put in originally, the same probability vector in originally comes right back out. That's because the Hadamard gate itself, when you apply it twice to itself, you get the identity matrix. So that's just an interesting math thing there. So moving on, this part is going to be a little bit funkier to understand, and that's because there's a bit more quantum terms and stuff like that, and it got things like Kets and things like that. And I'll probably make some videos on those topics as well, but it's not, the symbols look confusing, but they're not nearly as confusing as they seem, especially if you are familiar with linear algebra. This stuff is easy to pick up. So just basically think this as, I mean, yeah, it's a symbol, and in quantum computing, it effectively refers to the state of a qubit. It's just any arbitrary state, but it's defined as a linear combination of two well-defined states, which is, we'll get there. When you think of it as these are all abstract concepts, but when you think of it as a 3D model, the top and bottom of the qubit, which map to the arbitrary bits 0 and 1, so like a light switch, like it goes on and off. So in that same way, you know, if it's on 0, you get a 0 bit. If it's on 1, you get 1. But the cool thing, the entire idea of quantum is that it could be halfway between those two, or like a third of the way between one of them and closer to the other one. And then that changes the probability that's going to collapse to 1 when you measure it. So what we're looking at here, which is really interesting, is that the Hadamard gate causes superposition. So you're creating superposition with it, which is a really interesting notion. And also why the gate is particularly one of the reasons why the gate's so important. If we just move on here, we see that yes, this is basically how we define a qubit mathematically, and it's a linear combination of ket 0 and ket 1. And this basically, actually, interestingly, these are used as shorthand also to represent the top and the bottom because they're well-defined bases. But so they're kind of self-referencing in a certain sense. You'll see it later. You may see it in other places where they'll be like, you know, oh, well, ket 1's just the top. It's like, yeah, it is technically, but, you know, it can be a little confusing. It's kind of just a nomenclature. But what's important to understand is that basically psi is defined by some probability mapped to the first part and some probability mapped to the second part. So like if it were a coin that got 50-50, it would be 1 over the square root of 2 here and 1 over the square root of 2 here. And so you're probably confused about the 1 over the square root part. And again, that's to make the matrix multiplication work and all that stuff. Like, there's definitely more deeper linear algebra reason for why it is that way, but ultimately the math plays better if you do it that way as opposed to just putting 1/2 out in front. And it has to do with like Euclidean norms and all that stuff, is what's just linear algebra. So if you basically look at this part over here, the constrained term may be a little freaky, but it's basically just saying that these values, A or alpha, sorry, apparently can't type alpha, but anyway, alpha and beta are constrained by the fact that their positive value, so like their absolute positive value, must be a squared, and summed with the other one must be equal to 1, which means that basically at no point can you have a probability of getting 50 of heads and no probability of getting tails. That doesn't make sense. Like it wouldn't literally make, that just isn't a notion that makes any sense. There's no coin where you just have a 50% chance of getting heads and a 50% chance of getting nothing, you know? So you have to have a 50% chance of getting heads and 50% chance of getting tails, or you can have a 100% chance of getting heads and no percent chance of getting tails. That's fine, but it always has to sum to 1, basically, and that's what we're looking at here. So when we decide to put our qubit into the 0 ket state, that's effectively just saying that we're saying that's 100% of the time going to be in this state and 0% of the time going to ever collapse to the other term. So Again, you can work this math out on a piece of paper. It's actually not super complex, but it looks funky. It's literally just substituting in place of the alphas and betas, and then just, you're like, oh, it works. There you go. Not surprising. It's like that something plus 0 doesn't actually turn into anything. So, that the 0 term times the 1 over here doesn't turn into anything. That's what I'm saying. Anyway, moving on, because that was a little bit confusing, I'm sure. I'm going to talk about the qubit itself, because I'm trying to help derive a mathematical understanding of what's happening, and to understand that basically everything that happens to a qubit is defined by these matrix operations operating on a set of probabilities. So the Hadamard is just one of these, and although we're kind of exploring this concept for the first time in this video, this is kind of repetitive stuff, so it starts to make more sense as you see it again and again with different operations. It'll help you kind of build an intuition about what's happening here. So if we're looking at the qubit itself, again, I've basically chosen to take my probability vector of 1 and 0, and I've mapped. This is another way of representing my probabilities as opposed to representing it like this up here. It is to basically say that the first one maps to the 0 and the second one maps to the 1. So when we do that, we get, we already elected to basically say that this qubit is exclusively in this position. So we expect that the top would be 1, the bottom would be 0. Now what's interesting, the Hadamard gate is mathematically, if we do this matrix multiplication here, you get this, which means now, again, you've got a 50-50 chance of getting both of them, so you're in a superposition. So I know it does kind of sound like I'm repeating myself, but I'm kind of working through the math to show you why I'm saying the things I'm saying. And so, again, it's equivalent to saying that alpha isn't basically the result you got changes your probability vector to say now that, yes, this is a new place right here, like this is a new location now, and alpha is 1 over square root of 2, and beta is 1 over square root of 2, such that this alpha squared plus, or yeah, whatever, absolute value of alpha squared plus the absolute value of beta squared equals 1. So, yeah, so that's still true here. We just have a 50-50 split now. And so this is how our qubit is actually in superposition. And again, if you were to apply it one more time, you would actually end up with the same probability, this, by itself. But we're not going to do it a second time because there's really no point. And so like I said, this is really math heavy and it's super hard to understand, especially if it's like your first time. It's like, and especially if you don't look at linear algebra regularly, you're like, oh, symbols and stuff, it hurts my brain, yeah. I mean, it hurt mine too. But the other way, sometimes there's these tools that can help you visualize these things. So like as part of, to help me learn this stuff, I actually built one of these tools myself to help visualize these operations. So I'm going to go look at that now, and then hopefully we'll help build you a bit more intuition about what's happening when we use the Hadamard gate. So here we are. This is the tool that I built, and it basically is a 3D representation of a single qubit. This is based on the model known as a block sphere, which you can look up. I'll go ahead and include a link to the simulator in the comments, so you can check it out yourself if you want. But I'm going to play around a little bit and try to get a better understanding of what's actually happening when you apply a Hadamard gate. So, as you can see over here, I know it's a bit funky, like it's a bit crappy colors, but whatever. This is basically spitting out the probability of ending up in the 0 state or the 1 state. So, you're probably curious about these other bases though, because all of these are bases. Like you got 0 bases, the 1 basis, the plus basis, minus basis, and yeah, moving on. So these are obviously your standard ones because they correspond to the x, the x, y, and z axis. But your common operations or gates, whatever you want to call them, on a qubit are usually rotations in some manner or another around the sphere. So the qubit can technically at any given time occupy some point, like its state can be represented by some point on the surface of the sphere. So you may be like, well, how is that possible that I, can only have a probability of like, a 0 or 1 if that's the case? Well, that's because when you measure the basis, you have different measurement bases, and what you're effectively doing is you're looking at it, and you're looking at it like from the side of and you're saying like, oh, well, it's all the way on the 0 and it's like not at all on the 1, so it's clearly always going to end up being 0 when it collapses. But if I were to measure in a different basis, like the plus or minus basis here, you'd say, well, it's halfway between plus or minus. So it's going to collapse at plus or minus equally 50-50. And then you can say the same thing about the I and negative I basis. It's like, oh, well, it's halfway between two of them, so it's going to collapse to either one, 50-50. So, that can kind of give you an idea of how these measurement operations work. You can technically measure in any set of basically points that are opposite each other on the sphere, but these are the stamped ones that are well defined. And like I said, that's because they map to the XYZ basis, or XYZ coordinate system better, a bit more intuitive and familiar. So if we basically play around with this, like I said, it has to do with the rotation. First of all, so like every operation is rotation. Most of your operations are going to do something simple like rotate around one of these well-defined axes. So you're like, okay, well, like the poly x gate rotates around the x-axis, the poly y gate rotates around the y-axis, the poly z gate rotates around the z-axis, and I'll make some more videos on those later, but that's all you really know about them for now. They aren't super complicated to begin with, but it's a rotation around this axis, so it'll take this point here and go like, whee, and I can actually show you. So like, the poly x gate is going to rotate around this red line, which is the x-axis. So we go, there it goes, it's rotating around, you rotate again, and I'll, probably cover another video, but at some point later, but, it's not complicated. But let's think about the fact that you can rotate around any axis, like I said, you just, typically it's going to be axes that are, these well-defined ones. So what about like the joint axis that is the z-x axis? Like basically it's this axis that runs diagonally through the 0, or like through basically this line and this line. So you're getting this 45-degree angle split between the two of them. So if we were to picture that line's running through there, so you look at it, it'd be coming out right about here, it'd be coming straight at us right now, basically. And so we're gonna look down this, right? And the reason I'm gonna show you this is because, like, for example, if I look at the x-axis and if I look straight down the x-axis and I click the poly x gate, it's going to rotate around the gate, as you can see. So you're seeing this circular rotation around the gate, or around the axis using this gate. So let's do something like look straight down this axis here, and I'm not going to get it perfectly right, because, more or less just kind of trying to figure out roughly what 45-degree angles is. But let's say it's looking at us right now, and you should be able to see it mostly. When we apply the Hadamard gate, it's going to do this rotation. It's doing a rotation around this axis. We're looking straight at. And we could see that it ended up at this halfway point, right? So this halfway point actually is now going to cause our probabilities to collapse to either 0 or 1. So like I said, if I measure halfway between them, I get 0 or 1. So it's like, oh, okay, 50-50. And so you saw how that rotation accomplished that. And again, you can think of almost any quantum operation as a rotation. It's just about understanding what that rotation is. So if we were to apply the Hadamard gate again, you can see it swinging back up. And as I said earlier, if you apply 2 successive iterations of the Hadamard gate, it will effectively apply the identity transformation, which is to do nothing at all. So it completed a whole rotation and did nothing at all. It ended up back where it was. So that can, again, kind of help you build this intuition. Like I said, I think this really sums up the behavior you'd expect from a Hadamard gate. It's definitely a really cool gate because, it's the one you're probably going to use the most often you're probably, maybe not the most often, but you're going to use it a lot because it's basically the gate you use to get into superposition of any kind. And in doing that, it's going to kind of become essential, understanding how it works and stuff like that. This is, more interesting than most of the other gates because most of the other ones are simple rotations. And this one is 2, but it does something that's less easy to comprehend, especially if you aren't thinking about visualizing it this way. So, like I said, definitely, if you want to, make sure to play around with this. Or even, if you feel confident, you could try to program one of these things yourself. This is what I did because I wanted to become more familiar with how this stuff worked. And honestly, kudos to you for, starting your quantum journey here. You know, picking up how these gates work. I'm gonna make more gates and like more videos about gates in the future, but this is absolutely a great starting point. Especially since you give you some intuition about what we saw the other day in my last video. So yeah, if you have any questions, definitely feel free to drop a comment, or just like and subscribe if you want to see more of this stuff. You know.